Till long day after, today I will discuss again the linear algebra. Today's goal of this lecture, today I will see some properties of idempotent matrix. Then I will prove these properties. At first see the properties of idempotent matrix. These properties are actually very important for any comparative exam. First, eigenvalue of the idempotent matrix are 0, 1 or both. And rank of idempotent matrix always equal to trace. Minimal polynomial of idempotent matrix x into x minus 1. Always idempotent matrix is diagonalizable. Determinant of the idempotent matrix is either 0 or 1 because the eigenvalue is 0, 1 or both. K is idempotent matrix if and only if k equal to plus minus 1. And a to the power k always idempotent matrix. Then a plus b is idempotent if ab plus ba equal to I minus a, always idempotent matrix, and product of two idempotent matrix is idempotent if ab equal to ba. I will prove this property today. Actually, these properties are very important for any comparative exam. Another property, if A is idempotent matrix, then always trace of A greater than equal to 0, less than equal to n. And we all of us know trace of A equal to rank of A, and nullity of A means n minus rank of A, and here rank of A equal to trace of A, so this is n minus trace of A. And if trace of A is greater than n or trace of A is less than 0, then A cannot be idempotent matrix. Then A cannot be idempotent. Always idempotent means trace lies between 0 to n. And the characteristic polynomial of the matrix is x to the power n minus trace of A times x minus 1 to the power trace of A. And n minus trace of A, since trace of A means rank of A, this is equal to nullity of A times x minus 1 to the power trace of A. And this is equal to x to the power nullity of A times x minus 1 to the power rank of A. Next question. How many diagonal matrices of order n are idempotent? A equal to diagonal A. Then A square equal to diagonal A square, A square, A square. That imply since A is idempotent, A square equal to AI, here AI whole square equal to AI, that imply AI square minus AI equal to 0. That imply AI times AI minus 1 equal to 0. That imply AI equal to 0 or AI equal to 1. When AI equal to 0 and 1, then these are idempotent matrix. That means possibility is 2. When A is n cross n entries and each entry is 1, then A square equal to NA. And when n equal to 1, then a square equal to a, and when n greater than equal to 2, then a square not equal to a. If a square equal to na, that imply 1 over n a square equal to a. That imply 1 over n square a square equal to 1 over n a. And that imply 1 over n a whole square equal to 1 over n a. Therefore, 1 over na type matrix is always idempotent matrix. That means if n cross n matrix is look like 1 over n up to 1 over n up to 1 over n, 1 over n, 1 over n, this type, then always A is idempotent matrix. And when A is 3 cross 3 matrix, such type 1 over 3, 1 over 3, 1 over 3, this type of matrix is always idempotent matrix. Okay. A is non-zero non-identity matrix, then idempotent matrix are look like such type. Also, here the entries only 1 and 0. Also, this type of matrix is idempotent matrix. Notice this is the upper triangular matrix and here the eigenvalue is 1 and 0. So, the matrix which look like 1k 0 0, k is any number belongs to integer, then this is idempotent matrix. This type of matrix is idempotent matrix. I hope my all viewers have understood how look like the idempotent matrix. Next I will see sum of two idempotent matrix may or may not be idempotent. Here given A is idempotent, so A equal to A square and B equal to B square. Sum of two idempotent matrix, that means A plus B whole square, is it equal to A plus B? Notice this is equal to A square plus AB plus BA plus B square. And if AB equal to BA equal to 0, then this is equal to A square plus B square. Otherwise, this is not true. That means when AB equal to BA equal to 0, then sum of two idempotent matrix is idempotent. Next, product of two idempotent matrices. Product of two idempotent matrix always not equal to idempotent. Here AB two idempotent matrix, so A square equal to A and B square equal to B. Their product means AB whole square, we have to show this is equal to AB. AB whole square means we can write this as AB times AB. Also by distributive law we can write this as A times BA times B. And since if AB equal to BA, then we can write BA equal to AB. B. Then this is equal to A square B square, and since A square equal to A and B square equal to, this is B. B, so AB whole square equal to AB, that means Product of two idempotent matrix is idempotent when AB equal to BA. Scalar multiplication is idempotent. A square equal to A, then KA square would be KA. This implies K square A square equal to KA, and when the value of K equal to 0 or 1, then KA is idempotent matrix. Property: if A is idempotent matrix, then always A to the power K equal to A. Because A square equal to A, then multiply both sides with A square, then this would be A cube equal to A square, and here A square equal to A. Multiply both sides with A to the power 4, A to the power 4 equal to A square, which is equal to A. A to the power 5 equal to similarly A square, which is equal to A, since A is idempotent. Similarly, we can always will get A to the power K equal to A. So, if A is idempotent matrix, then A to the power K equal to always A, where K belongs to natural number. Is idempotent, then determinant always is +1 and 0. Apply both sides determinant of A square equal to determinant of A, then this imply determinant of A square minus determinant of A equal to 0. And determinant of A square means determinant of A times determinant of A minus determinant of A equal to 0. If you common determinant of A, then this imply determinant of A minus 1 equal to 0. That imply determinant of A equal to 0 or determinant of A equal to +1. And when determinant of A equal to 1, then that imply A is non-singular if and only if A is invertible. When only determinant of A equal to 1, otherwise this is not possible. I hope my all viewers have understood this type of properties. Now I will see two operators. One of these is nilpotent operator and one is idempotent operator. T from vector space to vector space, and the operator is such type T of x1, x2 up to x5 equal to 0, x1, x2 up to x4. Then notice T square x1, x2, x5 equal to T of 0, x1, x2 up to x4, and T of 0, x1, x2 up to x4 equal to 0, 0, x1, x2, x3, x4. Similarly, T cube x would be, x means x1, x2 up to x5 would be 0, 0, 0, x1, x2 and T to the power 4x equal to 0, 0, 0, 0, x1 and T to the power 5x equal to 0, 0, 0, 0. Therefore, the operator T5 equal to 0, but T to the power 5 minus 1 is not equal to 0. That means this operator is nilpotent operator. Next I will see one idempotent. T from V to V, T of x1, x2 up to xn equal to 0, x2, x3 so on. Then T square means T of x1 up to xn equal to, this means T of 0, x2, x3 so on, and T of 0, x2, x3 so on means 0, x2, x3 so on. That means T square equal to T. That means this operator is idempotent operator when x1 replaced to 0 and after that this is x2, x3 so on, and this operator is nilpotent operator. x1 replaced to 0 and x2 replaced to x1, x3 replaced to x2 so on, x5 replaced to x4, then this operator is nilpotent. Next I will see VBA finite dimensional vector space and TBA mapping from vector space to vector space which is linear, and if rank T equal to rank T square, then prove that rank T intersection nullity T equal to 0. Since rank T intersection nullity T equal to 0, that means V is direct product of rank T plus nullity T. For this, we have to prove rank T intersection nullity T equal to 0. Let X belongs to rank T intersection nullity T. That imply X belongs to rank T and X belongs to null space of T. X belongs to range T. That imply there exists Y belongs to V such that T of Y equal to X and X belongs to null space of T. That means T of X equal to 0. Here I have got T of Y equal to X. Apply T both sides, then this would be T square Y equal to Tx. And here I have got Tx equal to 0. That means T square Y equal to 0. That means T of Y equal to 0. That means Y belongs to null space of T. That implies X equal to 0 vector. And this is possible. We can write this as, since rank T equal to given rank T square. So from this we can write T square Y equal to T of Y. Since T square Y equal to 0, so we can write T of Y equal to 0. That imply Y belongs to null space of T. That imply the vector X is only 0. Therefore, rank T intersection nullity T equal to 0. So we can write V equal to rank T direct sum of null space of T. I hope my all viewers have understood this is okay. Similarly, when A is idempotent matrix, then we can write V equal to range space of P, direct sum of null space of P. And for idempotent matrix, since null space of here A, since I have considered A is idempotent, null space of A is equal to range space of I minus A. So V equal to, we can write range space of A, direct sum of range space of I minus A. This is the properties of idempotent matrix. I hope my all viewers have understood. Okay? Oh well. Today I will stop here. In my next video I will discuss some more question about other type of matrix. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.